right, so we're going to look at finding limits using direct substitution, and then we'll also look at the graph to help confirm. Notice here that we have the limit as x approaches c. Notice that there's no left or right. It's just assuming both directions. Equals f of c. That means the y coordinate, okay? That means that the point is actually equal to the limit, okay? Now, I know that this is a parabola that opens up. Okay? That's a continuous graph. There's no holes, there's no asymptotes. Think of graphically the things that made finding limits a little bit tricky was jumps, holes, and asymptotes. That means that this is just a point on the graph. If I were envisioning tracing it and doing this limit graphically, the limit would just equal the point. That's it. It would just equal the point, which means you can just plug it in. Where is the y coordinate on this graph? 2 squared plus 2 minus 3. 4 plus 4 minus 3. 8. The limit is equal to 5. Where is this point on the graph? 2, 5. All this first set is saying is that the point, the y value, is actually equal to the limit. This happens when your graphs are continuous at x equals c. Continuous means you're not lifting your pencil to draw the graph. You just you trace the graph right through the point. Okay? B. I don't know what that one looks like. Okay? But if I have a point on the graph and there's no discontinuity there, it should equal. So try plugging it in. $14, $16, so we get 4. Minus 1/5. Okay, see, so I don't know what this picture looks like. I'm going to graph it to see what I get. No idea. For no reason. There you go, positive 1/5. I'm going to graph it just to see what kind of graph I get here. So y equals parentheses root 2x plus 2 minus 3, close it. Okay. Right, we did limits graphically, we did limits in a table. I'm checking my algebraic with one of those methods to make sure I got it right. Okay, 0, 6, I'm just gonna, okay. Does anyone else say invalid dimension? That means that your stat plots are on and you're trying to plot points that aren't there. So if you're in your y equals, see how my plot 1 is highlighted and so is my plot 2? Just unhighlight them so that you can't see them. Right? Make sure that the only thing you want to see is highlighted. I'm going to try again. Graph. Okay, so I do see an asymptote, but I see it at x equals 2. Notice I only need this to be continuous at the x value in question. That's 7. 1, 2, 3, 4, 5. So that's like here. That's the only spot I'm looking at. It seems continuous. I don't see an asymptote there. That means that the point, it's on the graph. All I'm going to do is sketch a little picture. Graphically, right, what I know about limits graphically confirms algebraically. If there's a point on the graph, that's where the limit is. Okay. See if you can do C and D. Sketch a picture to confirm your answer.
C is whatever number.
Yeah. So generically, C is wherever you're trying to find the limit of the x coordinate.
Whatever you can there. Yeah.
Should be pretty straightforward. Okay, when I'm graphing this, what is the y equals here? There's no print. It's just this. That's the graph. You're looking at this graph, which is mx plus b. It's just slope of 1 at -4. Yes, it's continuous, and there's a point on the graph. Means all I'm going to do is plug in the x coordinate. Okay, so it confirms graphically, right? You're just checking your work. It's going to get a little bit trickier, okay? So this one, that's why we review writing equations of lines. There's the origin. That's y equals 6. Right, it's horizontal line at x equals 0. The point is 0, 6. There's nothing to plug into. That's it. It's just 6. There's no x coordinate. The y coordinate is 6 as you approach x equals 0. Okay. Let's do A. First thing I want you to do is sketch a picture over here. I want to do this one graphically. We're going to start scaling back the checking because it gets to be a little bit tedious, and we're going to focus more on the algebra. So if this is the graph in question, I notice that there's a hole. Why is there a hole? There's a factor that reduces. Okay? What does that graph look like? Well, I'm going to say a hole, and you should be able to tell me where the hole is. Hold on. Don't yell. I replenished, right? You have new choices. Don't yell it. Where's the hole on this graph? Michael? Not 2, 0. Sammy? 2, 4. How did you get 4? Plug 2 into the remaining equation. Okay, so there's Reese's, Kit Kats, and the other stuff, and then there's Airheads and Starburst. Come cheers. Okay, what does this look like? It looks like a line, x plus 2, with a hole. 2, 2, 4. Okay, if that's my picture, what is the limit supposed to be? As x approaches 2, the limit is equal to 4, because that's what I see on the graph. Okay, kind of slow. I don't want to have to graph every time, and we're not going to. All right, so what I notice is I want you to do it algebraically. I don't want to have to graph every time, okay? So plug in 2 and see what happens. Right? That's what the first strategy says. It says plug it in. Oops. 2 minus 2 in the bottom, sorry. Okay. I get 0 over 0. That's indeterminate. 0 over 0 is not a number. It's indeterminate. Is it undefined? Is it 0? Is it 1? It depends on what kind of pattern you want to follow. Okay, so it's indeterminate. Dividing out factors. When you get 0, 0, this means that the graph has a hole. Okay? When the graph has a hole, it means that you divide out the factor. Look at that. Okay, so my first step is I always check. Okay? Check x equals c. Okay? In this particular section, you're going to get 0 over 0. That means that you have a hole. Okay, so reduce. Right, divide out the factor and then try plugging in again. Okay, so let's reduce it. Now, this is kind of important for the notation. You should still write the limit statement as you are reducing. You should write the limit statement all the way up until you plug in the number. And so this is really 2 steps. Right? I did a lot of extra work to explain what was happening. This is what you need to see. Well, technically, I need to know it's 0 over 0. Now I can plug it in. 2 plus 2 equals 4. The limit equals 4. Okay, I don't want to graph it, especially by hand. Okay, so let's see what we can do for B down here. First step, check it. What do you get? Check x equals -3. Oh, well, the first thing I notice is that I'm dividing by 0. Nine minus 3 minus 6. Okay, 0 over 0. That's not an answer. That means there's a hole in the graph. There's a hole at x equals -3. Okay, second step. Factor and reduce. Notice that my notation, right, this is the problem that I'm trying to evaluate. That's what I'm going to keep writing. X plus 3x minus 2. Notice that x equals -3 is the whole. Look at the factor that's crossing out. The x plus 3 factor, that's the one that's connected to the whole. Okay? The limit as x approaches -3, write down whatever is left. It's just x minus 2 over 1. Okay? Last step, plug in -3 again. What's the limit equal to? -5. This is what you need to see. Check the coordinate. Decide there's a hole. Factor, reduce, plug in. All right, try C. You can use your calculator to help evaluate, that's fine. But you've got to check. Don't just factor and reduce before you decide what you're doing. Bless you. Aiden, check your fraction and see. Did you get 1/7? Okay. All right. There's my answer. All right, look at my notation. I did keep my limit statement once I started trying to evaluate. Could you check it by looking at a graph? You could. Now, when I check it, right, I'm not going to graph it by hand. I already know that there's supposed to be a hole here. When I graph it, I'm not going to plug in this version. I want to plug in the reduced version, but okay, I'll try both. X minus 3, because maybe I was having troubles factoring. Plus x minus 12. And I hit graph. Your calculator is not going to show you a hole in the graph. It's not going to happen. Okay, let's see, can I do second trace value? I could try 3. It's undefined. That means there's a hole there. So what if I just move a little bit to the left, a little bit to the right? Okay, let's hit trace. It's around 0.13, 0.12, right? That's what it looks like it is. Okay. What's 1/7? 0.14. Yeah, so the graph does confirm that that's the place where it is. But there is a hole in the graph. You just can't see a hole in the calculator. Okay, let's do D. Oh, yeah, I don't feel like plugging in 2/3. So 2/3 store for x. That's fine. 3x minus 2. Okay, I get 0. 3x squared minus 5x plus 2. 0. That's fine. Just show me that you checked that it's 0/0. It's okay if you use your calculator to do that. Okay, second step. I need to factor and reduce where that hole is. It's a good bet, guys, that 3x minus 2, which is the 2/3 factor, is going to be one of the factors you need to reduce. So start there. 1x minus 1. I want to check it, right? First, minus, plus. Yeah, okay. Notice my notation. Okay, now I'm ready to plug in. Two-thirds minus 1. Okay. 1/x minus 1. So I still have x stored. Minus 3? Okay. Equals -3. I'm just curious. 3x minus 2. Okay. We'll look for x equals 2/3. Okay, not expecting a y coordinate because it's a hole, but if I trace, okay, 2/3, can I get it close to 2/3? No, because the pixels don't get close enough. Okay, trace, let's try a value, 0.6. 0.6 was kind of close. Okay, -2.5. Oh, trace. It's kind of between -2.7 and -6.7. Your graph doesn't get very close, but at least -3 is between those two coordinates. Okay, turn your page. Right, that's just factoring, reducing, even though we got a hole each time. Okay, I see radicals. First step, guys, check it, plug in 0, see what happens. Except I don't know how to factor with radicals. So I'm not going to. But I still have a hole in the graph. Right? Every time you get 0 over 0, there's a hole in the graph. It means something should factor and reduce. Oh, something should reduce. I don't know how to factor that, so I'm not going to factor. But I am going to use something called a conjugate to try to reduce this. Okay, so conjugates result in no radicals when multiplied together. Kind of looks like a difference of squares pattern. First, outer, inner. Cancel out. Root times root. Well, it'd be nice if I could get this expression to have no radicals. Maybe then I could factor it. And so instead of factoring and reducing, we're going to use a conjugate, and we're going to do this thing that's called multiply by 1. Anytime you want to write an equivalent statement, you can multiply by 1. But in our case, our 1 is going to be a fancy form with the conjugate. Now, it doesn't matter whether you use the positive portion or the negative. You're just going to pick the same thing. All right, so let's rewrite our limit statement. Okay, here comes the new part. Okay. Well, the part on the top, that's the part I don't know how to factor. That's the part I'm going to use the conjugate for. Root x plus 1 plus 1. I would like them to be opposite signs. The opposite signs are the only reason that inner and outer term cancel out, and you're left with no radicals. That's the part I'm trying to get rid of, is the radicals, so then maybe I can factor this. Okay. Just FOIL the top. Don't multiply this bottom piece out. Okay? Leave it. All I want you to do, first, outer, inner, last. Okay? Notice I'm keeping my limit statement. Leave the denominator alone. Okay? Notice that x equals 0 was the thing that gave us 0 over 0. That means the whole happens at x equals 0. That's what that means. Which means this is the thing that I'm trying to reduce. I need to reduce the factor that corresponds to the whole. Okay, so first, outer, inner, 0, minus 1. I only did the grouping symbols just in case I had a negative that needed distribution. Okay. Just x in the numerator. Look at which factor is reducing. Okay. You're only trying to multiply the conjugates together because those are the two pieces that simplify nicely. Okay, there's my reducing. To a 1. Now you plug in again. I just had one more line here. That's okay. 1 over 0 plus 1 plus 1. 1/2. Okay. Just to make that clear, the hole on the graph is at 0, 1/2. Anytime you get 0 over 0, that means there's a hole. Look at what factor reduced, x over x. That means the whole is at x equals 0. Okay, I'm going to work down because I see a weird order down here, and then we'll go back and try B and C, or B and D. Okay, first check it. Plug in 10. 0 over 0. There's a hole. Can't factor with radicals, so I'm going to try the conjugate instead. Okay, the limit as x approaches 10 okay, conjugate. Just putting my grouping symbols here. And fancy form of 1. Notice that this one has a minus, so we are going to use a plus. All right, let's see what happens. Notice that I only actually multiplied the pair of conjugates together. Okay, the limit as x approaches 10. Before I even get there, I know that the whole is at 10. I already know that from the first step. I already know that's where the whole is. That's the factor I'm trying to reduce. Okay, so in the numerator, I get x minus 10. I don't get that. I get 10 minus x. Well, if you want factors to reduce, put them in the same order. All right, standard form. Put the x's first. Okay. Well, they're almost the same except this x is negative, so I need to factor that negative out. Now, I don't want to write this over again, so I'm just going to write that part, right? All I did is I factored the negative out. Okay, right? Because I want this piece instead. Now I see the reducing. But there is still a negative there, so don't lose it. Okay? And there is a 1 on top. And plug in. 1 over negative 1 times 10 plus 6 plus 4. What's the limit equal to? Negative 1/8. Okay, right, I showed a lot of steps in here. If you can simplify your algebra faster, go for it. Okay, I just didn't want you to miss any of what I did here. Notice, though, that I wrote my limit statement until I was ready to plug in. Right there. Right? Only after I started plugging in the number did I stop writing the limit. All right, you got B and D. And that's where we stop, right? That's where we're stopping, B and D. Try them, see what you get. You can try them in a table. You can try them graphically, but you should be able to check your work. It's really easy to lose a negative somewhere, so make sure you can check your work. Does someone want to come and write up the answer? You do? Go for it, Kelly. Go for it. Come on. It's pen. Yeah, come write it. Yeah, you can do it. You can bring yours up. You just bring yours up then. We'll just put yours up here. Okay. Yeah, you can just slide it under. Go for it. There we go. We'll just cover the second one. Okay.
It's light. Sorry. I can write it again.
Hold on.
Oh, there it is.
There we go. You just got to adjust it. Okay. Focus. Okay, so the limit as x approaches 3. The notation is good. Multiply with the plus. Okay, see that? X plus 1 minus 4. Guys, you already plugged in 3. That's the factor that has to reduce. If for some reason you're not getting that factor to reduce, then you messed up the multiplying. Okay? and then you have just root x plus 1 left. So there's only one other thing I would show, and that is maybe root 3 plus 1 plus 2, right? I would just show that I was actually plugging in 3. Yeah, okay. Go for it. Does anyone have C? And then just so that you know, there is a hole at 3, 4. In case you were trying to check graphically, that's what you'd be looking for on the graph if you were tracing it. Okay, D. Any volunteers for D to bring it up? Yeah, Aiden, come on. Okay, here you go. Just slide it underneath. Perfect. Okay. All right, so we have the conjugate, root x plus 2. Okay. And notice that the order is a little backwards. Rewrote it with the negative in front, so that's good. And then he factored the negative out. Okay. Multiplied the conjugates on the bottom. Root minus 4. You're not going to see that reducing factor unless you actually reordered and took your negative out. Okay, there's the factor that reduces. Okay, you're left with the negative in front. So don't lose that. So the only thing I would show, you didn't show me plugging in. I would just make sure that you can see that you're evaluating. So let's try that. Negative root 4 plus 2 over 1, right? There's the plugging in. Right after you evaluate, right, you stop writing the limit statement. Okay, so the hole is at 4, and we get negative 4. That way you can check graphically. Knowing how to interpret this graphically is helpful. You can also try doing it in a table. Try 3.999. Try 4.0001.